All right, today we'll cover a couple of theoretical results. The first one is the Markov inequality. We've already seen Chebyshev, but Markov should be used actually to prove Chebyshev. And we'll do a simple example using Markov, and then we'll see the law of large numbers. Okay, so Markov gives an inequality, which is then used to prove the Chebyshev inequality, which we saw when we were talking about expectation and variance and how that relates to distributions. Okay. All right, so the Markov inequality says that if you have a random variable and it's only taking non-negative values, okay, so then the expectation will also be non-negative, right? And of course, we never want probabilities to be negative, right? And A is a positive real. Then the probability that X takes a value bigger than or equal to A is less than or equal to the expectation of X divided by A. Okay, so we've got, let's go through this. It's fairly simple. So what's the probability that X is greater than or equal to A? Well, if I had a PDF, then that's the integral from X going from A to infinity, PDF evaluated at X dx. Okay? Now it's convenient. We'll divide by A outside and we'll bring an A inside. Okay? Now, X is taking values from A to infinity. So A is less than or equal to X. Okay? So I can replace, if I replace the integrand by something which is greater than or equal to the previous integrand, then this integral will be less than or equal to that integral. Okay? Now, X, if I integrate X f sub X dx from A to infinity, and X is always taking positive values, right? Then that's a subinterval of the interval from 0 to infinity, right? So then this integral is less than or equal to this integral with the larger interval of integration. Okay, but this is 1 over A times, by definition, this integral is the expectation, because X is not, we said X is never taking values less than 0. So that would be the same as the integral from minus infinity to infinity. So that has given you the expectation. So if X always takes values bigger than or equal to, if X always takes positive values, then the probability that X is bigger than or equal to some positive number of A, that's less than or equal to the expectation of X divided by A. Okay, so that's the Markov inequality, which we're going to use to prove the Chebyshev inequality. Okay. So the corollary to Markov is that if you have X taking non-negative values and with some finite expectation, and A is some positive real, then the probability that X is bigger or equal to A times the expectation is less than or equal to 1 over A. Okay. So let's say I have incomes within the city or within the country. I have people's incomes. Now those are greater than or equal to each individual income is greater than or equal to 0. Okay? And there's some expectation, there's some distribution for that. I don't know what it is, but there's some distribution for that. And that distribution has some expected income. Okay? So what does this say? This says that the probability that x is greater than or equal to a times the expected income is less than or equal to 1 over a. So the probability that I earn more than 100 times the expected income is less than or equal to 1 over 100. So less than 100%, less than 1% of people will earn more than 100 times the expected income. Okay? Yeah. Okay. All right, so we already did that one. Okay, let's do a slightly longer one. Okay. We'll see how this ties into things like surveys of opinions. Okay, so there are small n voters. We want to estimate how many of those small n voters will vote for the BRP. Okay? Well, there's too many voters in Lahore, right? Millions. Can't ask all of them, right? So, what I could do is I could go and I could take a sample of maybe 1,000 voters, right? And I could ask them, and I would probably do my best to make sure that people I'm asking are independent of each other. I'm not going to ask a group of friends at McDonald's how they're going to vote, because they might tend to vote the same way, and so on. So I do my best. But even if I do my best, I'm still concerned with the question that I asked 1,000 people, do they represent 5 million voters? Is their opinion close to the opinion of 5 million voters? Can't ask all 5 million, but when I do a survey, I'm sort of supposing that the survey is representative. So is there some way of quantifying how representative that is? Or how likely it is, for example, that I have a bad sample which isn't telling me what the voting intention overall is. Okay, so this is what we're doing. We have survey results, but we have to interpret them. Right? Okay, so there's small n voters. Probably should have done this the other way around. Small n is the total number of voters. Capital N is the survey, right? I took capital N voters out of those very many small n voters, and I asked for their voter intentions. Okay, so out of the capital N people that I asked in my survey, B of them say that they will vote BRP. Okay? And then I go back to my boss at the BRP, and I say, the fraction of people in this city who are going to vote for you is approximately B over N. Okay, so so then the question, plus the probability of the other die rolling a 2, plus the probability of the other die giving a 3. Each of those is 1/6. maybe I should, right, fair die 3, 6. Okay. All right, so that's an example of using the cumulative conditional probability mass function. Okay. Yeah. Yeah. The
it would just be 1 over 6 into 1 over 6 divided by 1 over 6.
Yes. Yes. Each one of those probabilities is 1 over 6. Okay. Now, if we have, in that case, we had 2 discrete random variables. So they had a conditional PMF and a cumulative conditional PMF. Now, if you've got continuous x and continuous y, so each one has its own PDF, right? And then you have its conditional PDF, which is the probability density, not the probability, the probability density for x given y. And then if you want the cumulative conditional probability, right? This notation means the probability that x is less than or equal to a, given that y is definitely equal to b. So you take the conditional PDF for x given y. The y is fixed at b, and x is ranging from x is taking values from minus infinity to a. So let's say we could call that t, and so t is going to take values from minus infinity to a, right? And that gives us this thing there. Okay, so that was this was the material that was left over from the previous session, and then there are some exercises that you should do on your own for the for this conditional probability idea. Okay. 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 Then we go on to moment generating functions. Okay. So we've already done with moments. I may not have used the word, but we've already talked about moments. So the expectation of x is the first moment of x. When we did variance, we needed the expectation of x squared. The expectation of x squared is the second moment of x. Now, we won't always be, in this course, we're not going to really discuss the other moments, like expectation of k would be the kth moment of x. But if you do another probability course or another statistics course, then the higher moments become important, right? So moment generating functions are a way of algebraically extracting moments of functions and avoiding doing the summations or the integrations, which can be challenging, right? So moment generating functions are a way of generating all the moments of a random variable, okay? And doing it in an algebraic manner rather than using summations or calculus. Okay? So, this is the expectation of x to the n is the nth moment of x. We've already talked about the expectation of x, the first moment, and the expectation of x squared when we were talking about variances. Okay, but if you want, if you do further discussion of probability and of statistics, Then we also talk about skewness and kurtosis, and they would require the calculation of fourth moments, for example. Right? So, turns out that moment-generating functions can give us a way of extracting moments in an algebraic manner, which is sometimes easier than doing the direct integrals and sums that we've had. Okay? All right. Generating functions in general are formal power series, and within that power series there's some way of encoding some information that you like, and then you do algebraic manipulations on that to get out the information that you want. Okay, in general. Right? And in our particular case, we're looking at extracting moments. So, I'd like you to, we're going to be using this a number of times. So I'd like you to recall the Taylor series for the exponential function, or e to the x. If you want to write it as an infinite series, you can write it like this, right? 1 plus x over 1 factorial plus x squared over 2 factorial plus x3 over 3 factorial, and so on and so forth. You can write it as this infinite degree polynomial, or this infinite series. Okay? Well, hopefully you saw that in Calculus 2. If you didn't do Calculus 2, then, well, now you know. Okay? This you'll need to know, yes. Yeah. Okay. All right. So the idea is if you want to, so for any real number, if you wanted to know what e to the x is, or what the exponential of x is, you'd put in that value of x, and you'd sum up all these infinitely many terms, and it would give you the exponential of x. Okay? All right. Now we define the moment generating function. All right? Remember we talked about expectations of a random variable, variances of a random variable, and so on and so forth. So I have a random variable x, and what I do is I take my function of x is exponential of tx. Okay? So I had a random variable x. I invented a new random variable, exponential of tx. Now, I calculate the expectation of this new random variable. I call that and when I do this, when I calculate the expectation, I'm supposed to be doing either a sum or an integral. So I'm going to sum out, or I'm going to integrate out all the x's, and what I'm going to be left with is a function of t. Once I do this, I'm going to be left with a function of t. And that function of t, I write as m sub x of t, and that is the moment generating function of x. Okay? Okay, so far that's just formalism, but we'll see in a bit how I can then use the moment generating function to find the moments of x. Okay? But for now, let's say this is just a definition. Okay? Okay, now this e to the tx, right? So e to the tx is what? E to the tx is this infinite series. Well, it's either, if you know how to calculate e to the tx, that's fine, right? You replace x by tx in here. If you can calculate e to the tx on your calculator, all right. But in principle, it is this infinite series. Okay? Now, infinite series, sometimes they diverge off to infinity, and sometimes they converge. right? So you will, even if you didn't do calculus 2, you've seen the geometric series, right? Right? So the geometric series converges for some values of x, right? 1 over 1 minus x is equal to 1 plus x squared plus x cubed. That's the geometric series, right? So that converges for some values of x, and it diverges for some values of x, right? So it doesn't converge for x is equal to 1, for example. So when you're dealing with an infinite series, you might have some time, okay? Why? Because Chebyshev will also talk about variance. Okay, so we already had Chebyshev, but let me. Okay, so if x is a random variable, it has its expectation mu and its variance sigma squared, then remember that the probability that x is taking a value more than a standard deviations away from the expectation is less than or equal to 1 over a squared. Okay? Okay, so for example, if we were talking about two standard deviations, the probability that x takes a value more than 2 standard deviations from its expectation is less than or equal to 1/4. Okay? And okay, so we've seen that before, but now we can use the Markov inequality to actually establish that result. So first note that being more than a standard deviations away is the same as saying that the square of how far you're away is bigger than or equal to a squared times sigma squared, right? And recall that the variance is equal to the expectation of x squared minus the expectation squared. And so when you look at it when you square things, right? The square of how far you are from the expectation being bigger than or equal to a squared times the variance implies that the square of how far you are from the expectation is bigger than or equal to a squared times, write the variance in terms of expectation of x squared minus mu squared. Okay? And expectation of x minus mu all squared is that again. Okay. And now we can use the Markov inequality, and we get the Chebyshev. Okay. Don't necessarily want you to remember all of that, but I want you to know that there's a reason for it, and the underlying reason is Markov. Okay, so once again, the probability that you are more than a standard deviations away from the expected value is less than or equal to 1 over a squared. Okay, let's apply that. Okay, so if we go back here, let's replace a by a over sigma. And if we do that, then we get a corollary of Chebyshev that the probability that you are a certain distance away, that the distance you are on either side from the expected value, the probability that you're bigger than a distance a from the expected value is less than or equal to the variance over a squared. Okay. Okay, so we will use that corollary as we go forward. We return to the example of the survey. Okay? I'll remind you of a few things. The expectation of each xi was p. The expectation of the square of xi, well, it's 0 squared times the probability of 0 plus 1 squared times the probability of 1, which is p. And that turns out to be equal to p. So the variance of each xi is the expectation of xi squared minus the expectation squared. So it's p minus p squared, which is p times 1 minus p. Okay. All right. Now, when we did our survey, we should have taken care that the xi's were independent, right? We don't go to a wedding where there are 100 related people and ask them, right? Because their views might interest each other. They might tend to go more in one way or another. Okay? But, okay, if we assume that the xi are independent, and once again, b was the summation of the xi's, and expectation of b was np, we found. Now, if we go through the variation of the b's, the variation of b, which is the variation of the sum of the xi's, and the xi's are independent, right? So we get np times 1 minus p. Remember, capital N is the number of people in the survey. Okay. Now, we apply the corollary to Chebyshev's theorem. So what are we doing? We're estimating b over n. P is the actual fraction of people who are inclined to vote for the BRP. The probability that this b over n is more than epsilon away from the actual value is given by the corollary. Okay? Okay, so the probability that b over n, the difference between our estimate for p, b over n, and p is greater than or equal to epsilon. Okay, well, we can multiply through by n, right? So that's the probability that b minus np is greater than or equal to n times epsilon. Okay? Now, the corollary says that this is that the variance of b is less than or equal to the variance of b divided by this squared, n squared epsilon squared. The variance of b was np times 1 minus p, and that's divided by n squared epsilon squared. Okay, and you can decide. There's an n and there's an n squared, so let's divide by n. That's p squared over 1 minus p squared over n epsilon squared. Okay. Now, what does this say to you? Doesn't say anything. Okay. Once again, the probability that the estimate using capital N in the survey is off from the actual fraction of favorable voters for the BRP, that difference is bigger than or equal to epsilon, is equal to n squared over 1 minus p squared over n epsilon squared. So you can drive this down by taking larger and larger n. And this is remarkable because I have no idea about p. I have no idea of the what distribution, what PMF It is for voter preferences. But I can, if we estimate P and we get some big number over here, I can say, all right, look, okay, take twice as many people. Your bound on your estimate will go down by a factor of 2. Okay? All right, so that's one result which has important consequences. Now we go to another one. Okay, so let's say you flip a coin 4 times. The expected number of heads is 2. You get 3. Is that surprising? No. Flip a coin 400 times. The expected number of H's is 200. You get 3. Okay, you thought the coin was fair. Are you surprised? Is it impossible? It's not impossible, but it seems highly unlikely. Right? Okay. Okay, what if you got 2 25 H's? You'd probably be okay with that. Okay, so we have our expectation, this mathematical expectation. Then we actually did the experiment, right? And we got something. Okay? We have an expectation that 1/2 of the results should be H's. And then we have the actual mean. Right? We have the actual fraction that were actually H's. We're expecting mathematically 1/2 to be H's, and we're getting the actual mean, right? And we expect those to be close together. Right? We expect those to be close together. That's the idea of a survey, as we were discussing. I expect that if I survey enough people and they were independent, that is the fraction of BRP voters in that survey will be close to those that are expected. Okay? So, means and expectations and actual means after the experiment is done, they should be close to each other. Not exactly, maybe. They should be close to each other. Okay, so the laws of large numbers, they sort of say, well, yes, they will be. Okay, so the weak law of large numbers. If you've got x1, x2, x3, and so on, you've got this sequence of independent and identically distributed random variables, so that they're all the same. They have a finite expectation mu, and they have a variance sigma squared. Okay? Then, if I take n of these identical, independent, identically distributed xi's, I take n of them, x1 up to xn. And they take whatever values after the experiment is over. And I divide by the total number. That gives me a mean value. And if I subtract off the expected value for any of these xi's, I expect those to be close to each other. Okay? And what this says is that whatever tolerance you set on this for the difference, the probability that the sample mean the difference between the sample mean and the expectation, whatever tolerance you set, epsilon, no matter how small it is, the probability that this tolerance will be exceeded is going to 0 as n goes to infinity. Okay? So, if my PMF for my coin flip, just take enough coins, right? And you will get something which is your sample mean is going to get very close to your expectation. And if it isn't, well, just keep taking more and more coins, flipping more and more coins until it is. Okay? Okay. Alternately, we can write the same this way. The probability that the difference between the sample mean, I'm using bar to be the mean, that the sample mean differs from the expectation by more than epsilon, that's going to 0 if you let the number of these identical independently distributed random variables go to infinity. Yeah.
How are we calculating the sample mean though? Like isn't x1 a whole separate random variable?
Yeah. So let's say x1 is the result of the first coin flip, x2 is the second, and so on and so forth. They all have the same PMF, right? So if I take enough of those and then I divide by n.
How are you summing up the m's?
Well, the xi's will take some value 1 or 0, let's say, or whatever values the xi take, right? And I take each one of those values, add them up, and divide by n, and that's the average of the values. Yeah. Okay. All right. Or the other way of looking at it is, if I take the sample mean, the difference between the sample mean and the expected value, the probability that will be less than any tolerance that you set. In the limit as n goes to infinity, you're guaranteed that this will be within epsilon of the sample mean will be within epsilon of the expected value. Okay? All right, so if we believe the result from Chebyshev, we can prove this. I'm not that interested in this class in the proof. I can read through the derivation if you're interested. The important thing is this result, right? There's a point to doing surveys, basically, right? And the weak law of large numbers is justifying our idea that sample means, if the sample is large enough, should be close to expectations. Okay. The strong law of large numbers is the other law, which sort of gives us the same basic intuition. The strong law can actually be used to prove the weak law, but not the other way around. And the strong law says that under the right circumstances, this is a little bit different. This is a little bit different. The limit sign is inside the probability rather than the outside. Okay. Don't worry too much about it. That's something we discuss more in another course, in a more advanced course. But so it's actually a non-trivial thing to put, where exchanging limits and integrals or limits and sums is not trivial. And it also requires a bounded fourth moment, which the weak law was not required. But I think at this level for this course is basically, for us, it's saying the same thing. Sample means if the sample is large enough, should be very close to expectations. Okay. All right. So as I said, that you can actually prove the strong law with what we have. So you can prove the weak law with what we have using Chebyshev. So you would do Markov, then Chebyshev, then the weak law. But doing the strong law is too difficult at this point. We don't know enough real analysis to do that. Okay. All right. So just, I guess, the justification that what we're doing mathematically actually has a relevance to the real world, right? When we do these experiments in the real world, those means should be close to the expectations that we calculate. Okay, see you next week.